Okay, I think we should start right now because we have a small time frame. So for the people who are here, I am going to be hosting this session. I am Shay's sister. My name is Shaheer Niazi, and I will be moderating everything that's going on. As I was saying before, we are a group of students, so there will be some technical difficulties, and we hope that you can bear with us through this time. So yeah, I would first like to ask Shahir to unmute and tell us a bit about himself, give us an opening. I will be disabling chat and video sharing until the question answer session starts.
Okay, hello people. I am Mohammad Shaheer Niazi, and I am right now a bachelor's student studying physics at the Institute of Space Technology in Islamabad, Pakistan. So my background is pretty much in physics and in astronomy as well. I had an interest in astronomy since I was like at a pretty young age, and astrophotography also naturally was an interest which came along with astronomy. I also have a research paper in physics published in the Royal Society of Open Science, and this was, I think, in 2017. So yeah, physics kid and doing astrophotography at my university, the Institute of Space Technology. So Khadija, can you allow
Yes,
me to share my screen?
1 second. You can share your screen now.
Okay, hold on.
Okay. While we're waiting, I would just like to give some background on Shay's astronomy interest. He did start out watching documentaries as a young child due to our parents, our father and our grandparent. They were both really interested in in like space, and they would teach us both about astronomy. And Shay is the one who started taking interest in that. And before you start, Shay, can you give us some information about what exactly got you into astronomy? Is it the documentaries? Is it the parental influence, or is it something else?
I think it was a mix of both, a mix of everything, and my general curiosity towards using equipments and using basically things like telescopes. So my father got me a telescope. It was a toy telescope, so I got it when I was like I think around 8 or 9 years old, and I saw the moon with it, and I was pretty fascinated. And ever since that, I always had a need that I want a bigger telescope and proper equipment for taking pictures of the cosmos. And recently, I have gotten that opportunity at my university, the Institute of Space Technology, and finally, after so many years, I've gotten to properly delve into astrophotography and astronomy as well.
Thank you. And you seem to have prepared something for us here. Is it going to give us some insight into what helped you get into astrophotography and the equipments you're using?
Yes, I'm going to go over a bit of the basics of astrophotography. I'm going to show you some of the examples of pictures I took in the start, how it started for me, and how it's going right now. And then I'll give you guys a small demonstration of the processing, how to use the softwares, and how a proper image is created from using the data acquired.
All right, then the floor is yours. Help guide us on what it takes to become an astrophotographer.
Okay, so I'm going to start with this presentation here. It's not going to be long. So we all know that the first thing in anything, any photography is a camera. So we need something which can take pictures for us. It can also be a smartphone. It can also be anything, a small compact camera, anything that can basically point and shoot a picture. In the past, people also used film cameras, like the ones with those film rolls in them. they used to use those to take pictures, but now technology has advanced pretty much that we can take pretty good pictures using these DSLRs. So this is my first, I consider this my first astrophotograph. So this was in 2014. So I used this camera over here. It was a Sony Cybershot. It's a pretty small compact camera for taking family pictures. We used it mostly when we used to go traveling and stuff. But I saw that it had a feature called exposure. So what exposure means is that it keeps the shutter open for a period of time and it can collect light for that time. And the limit of the camera was that it could do up to 30 seconds of exposure. So I thought, why not point it at the sky and see what I captured in the night sky? So I took these pictures, these 30-second exposures, and I combined them into one image. And what I could see is the motion of the stars in the sky. So what you're seeing here is actually star trails. And I posted this on the Lahore Astronomical Society page on Facebook in 2014. And I found it recently as well. I rediscovered it, that this was a picture I took, and looking back at it, I was pretty amazed on how far I've come with astrophotography. So we all know that a camera has, if you have all seen a DSLR, we can see that it has certain functions. So astrophotography is basically you have to point your camera at stars in the night sky. You have to capture the stars, you have to capture the small details which are hidden behind these layers of air pollution and light pollution and the atmosphere of the earth. So there are three main things which are important in astrophotography. So the first is exposure. Now in this camera screen, what you're seeing, the 1/4000, that's the exposure value of the camera, the setting. So this means that it's going to take a picture of 1/4000th of a second. So you can adjust this on the camera and it can go up to 30 seconds, 20 seconds, 10 seconds. And also you can keep it on for an indefinite amount of time, even though that's not practical. So the more the exposure, the more the light we are gathering on our sensor, and the more brighter our image is, the more photons are coming and the more data we are gathering. This also has some drawbacks, because if we have light polluted skies, that means the more the exposure, the more the light pollution will come in and saturate the image. That means at one point there will be more light pollution saturating your image than the actual data of the stars and the stuff you're trying to image. So we keep the exposure at a minimal value so that we get a balance of these two things. Also, the more the exposure, so if you're just setting up your camera on the roof and you don't have a mount, you don't have something to track what's known as a tracking mount. Basically, the sky is rotating around. So the earth is rotating, so the stars are moving in the sky. So if you go over a certain exposure, you get a picture like this. You get a picture where you can see the trails of the stars. So basically your image has smudged out. And to avoid that, what people use is tracking mounts, and those are mostly used in telescopes and more professional equipment. But nonetheless, if you keep your exposure at a minimal value, for example, 15 seconds to 20 seconds at a low enough magnification, you can get it, the star trails are negligible basically. The second thing which is important is the ISO. So ISO value over here, you can see on the screen is written ISO 100, and you can change this in the camera as well. ISO is the light sensitivity of the camera. It's how sensitive your sensor is to the incoming photon, the incoming light. So what we do is that in astrophotography, if you're using a DSLR, normally you keep the ISO to around a moderate value of 1000 to 1600, because the more the ISO you get, the higher the noise value in the image, the more noisy it becomes. And the lower the ISO, the less the noise. So you have to always keep a balance between these things, the exposure, the ISO. Now the third thing is the aperture. So normally when you using a DSLR, we use the M function, which is the manual mode. So you rotate the knob at the top and you select M. So I think the aperture usually stays constant. So the aperture is the how much open the shutter is. to the sensor. So the more it's open, the lower the f value, the brighter the image will be, and the smaller the f value, the dimmer the object will be. And this is also important with telescopes, more important with telescopes, because telescopes apertures are what basically govern how much light is being gathered. So a bigger mirror you have, the more the aperture, the more light which you will be gathering on your sensor, and the lesser time you will need to take an image for to get a certain brightness. Now, the process of taking astrophotography, to taking space images, to taking images of the stars. So over here we can see that we have a basic setup. We have a camera which has a lens attached to it, and it's pointing at, so this is the Orion constellation, and I will show you a few examples of the Orion constellation as well. So the Orion constellation is a pretty famous target to image because it's pretty easily recognizable, and it actually has a nebula, the Great Orion Nebula, at the bottom center of it. So when we take pictures in astronomy, what we do is we take three sets of images. So our main set is the light frames. So light frames is what it means. Light frames. You're taking pictures of the object you're seeing. You're gathering light. Now that image will have a lot of noise. It will have a lot of light pollution in it as well mixed in. So what we do is we take calibration frames as well. Now the two types of there actually three types of calibration frames. The more basic ones are the dark frames and the flat frames. Now in the dark frame, what we do is that we take the camera and we cover the lens, we cover the shutter, and we take the same amount of exposure with no light coming in. So that basically generates a picture of the thermal noise in the camera and the general sensor noise which is being accumulated. The flat frames is a process. It's a more difficult process, but what it does, it helps in removing the effects of light pollution. It removes the dust particles, which can cause some effects on your sensors. I will show you a few pictures as well, which will help you understand what flat frames are. So
Just
how you take
like
flat frames.
before you continue, could you tell them, with regards to the settings you mentioned before, how would you differentiate between light frames, dark frames, and flat frames?
So lights and darks are taken with the same settings as you took with the same settings. Flat frames are taken in the same setup which you use. So you have the same focus, you have the same camera, you have the same lens attached to it. But what you do is you take a certain exposure with a flat field, and you cover the camera lens with a white cloth or a white t-shirt. So you have a flat field coming in it. And you adjust the exposure. It's a more difficult process. You adjust the exposure accordingly so you get a decent enough image. And you have to experiment with that. You experiment around with it, you tweak it around, and you find out what's best for your image. So when you combine all of these three types of frames into a software, so it's a process called stacking. Stacking because we take multiple light frames. So for example, if I took a single image of 15 seconds and I combine 100 of those 15-second images, so I will get a total exposure equivalent to if I took a single image of 1500 seconds. So that is the process of stacking. Instead of taking a very long exposure and having a lot of noise in the image, what we do is we take many small second exposures so that we can combine them and get a low noise image. So after though you put these in the stacking software, it removes the light pollution, it removes the noise, it removes any artifacts of dust and other effects of the lens. And then you have this final image which you can process and bring out the certain object in. So for example, this is the Orion constellation, just like in the diagram before. And this is what I took with the DSLR. So what I did in here is that I just put the DSLR on my wall, and I had it pointing to the Orion Nebula, and I took many pictures of 15 seconds each, and then I combined them all into this 23-minute picture. So this is the equivalent of if I had let the exposure to 23 minutes. If I let the camera gather data for 23 minutes, this is the equivalent of that, but with much lower noise, and it's a much cleaner image. you can actually see the nebulosity of the Orion Nebula in the middle, and you can see the Flame Nebula up here on the top. So this is what a DSLR image typically looks like, and it's still not a very good image. You can still see a lot of color noise in it, and there are many other problems with it as well, which are fixed with much better calibration frames. So if you have your calibration frames much better, then you can avoid these sort of noisy effects in it. And this is without tracking, so this is no mount, no nothing. The software aligns these images themselves, and I'll show you that process when I go onto the software. Here is so this is Venus, and this is also taken from my home roof using a DSLR, and it's a 3-minute total exposure taken using 15 seconds frames. So this is an example of light, dark, and flat frames. So you can see in the light frame that we have our object which we are imaging. It's not very prominent, and there's this halo of light around it. So this halo is basically the light pollution. The sky is light pollution, and you have the lens, its own effects, which is causing this halo to form. So this is a one picture which is worth 20 seconds. And if you see the flat over here, the flat image is only the halo. So it only has the glow of the light pollution. It only has the glow of the sensor and the basically effect of the lenses on it. So, and this is a dark, you can't really see much on it because, well, it's a DSLR pixel has so many pixels that you won't really see the noise, but there's a lot of noise in this picture right now over here. So if you combine all of these pictures into a processing software and you stack them and you remove the flat field and you remove the noise, so this is a final image which you can get. So this is the Orion Nebula, and you can see it's pretty prominent over here. There's no light pollution. There's no the halo, that halo is totally gone. There are still some artifacts, but that is due to the DSLR's difficulty with DSLR imaging. But nonetheless, it is a pretty good image. And this is using a telescope. So this was the same the nebula, Orion Nebula, using just a DSLR. And this is the nebula, which is zoomed in using a telescope, with also with the DSLR. So if we talk about stacking software, so these are like the three primary stacking softwares which I have used. So we have Registack 6. So this software is more for doing planetary imaging, for doing images of the sun and the moon and all the objects on the moon. So it's more for planetary imaging. For imaging objects or like deep space objects, we use this thing called Deep Sky Stacker. So it's a pretty good software which focuses more on the deep space objects, nebulas, galaxies, and it works pretty well with your DSLR images. Now, there's another software which I'm using primarily is CCD Stack 2. So this is more for astronomy dedicated cameras, and I will come to that in a bit. So this is our setup at the Institute of Space Technology. So this is me standing with our primary telescope, which is a 16-inch Meade telescope. It's a Smith-Cassegrain telescope with a mirror in it. So the light comes in, it bounces off this convex mirror, it's reflected off a secondary mirror at the top here, and the light goes through it down to the end of the tube, where we either put an eyepiece or we can put a camera. So this box type thing over here is actually an astronomy camera. So this is from a company called SBIG, SBIG, and they're based in America, and they make pretty amazing astronomy cameras. So the dedicated astronomy cameras have a benefit that they have a CCD sensor. So a CCD sensor is usually better for astrophotography because it offers a wider range of wavelengths to collect, and it offers lesser noise, and you have a smaller focal view, field of view, and different kind of things which are more preferred over DSLRs. One specific thing about this camera is that it's monochrome. So that means it does not collect color unless you put a filter on it. So all the images taken from it are black and white because it doesn't have any color filters on it. It collects all wavelengths irrespective of the color. What a DSLR has this matrix of LRRGB filters on it, which basically are on top of. So it has color filters on top of each pixel, which then collect the color and then combine it into a color image. But this one, it just has a sensor to collect photons, general photons, which range usually from the near ultraviolet till around the infrared range. So these are the images taken using this camera and that telescope. We use stacking as well. I used all the same procedures I've told you. The only difference is that I have a telescope and a dedicated camera. So you can see most of these images are in black and white, but this image here on the top left is in color. So we can take color images from a monochrome camera. The only thing we have to do is that we have to put a color filter on top of them. So in this particular instance, you use a red, green, and a blue filter, and you collect individual data for each color. And in Photoshop later for post processing, you can combine those color images into individual channels. So you put the red channel, the red data into the red channel, the green data into the green channel, the blue into the blue, and you can combine it into a multicolor image like this. And this is actually a small part of the Orion Nebula. So as I told you, the field of view of the camera is pretty small, so we can get into the details of pretty of big objects, and you can get smaller objects like these galaxies pretty detailed as well in this. So now I'll go on and show you guys a bit of the process of stacking.
Yes,
So here
part
I
of the
have
software as well.
what?
Please show us the software you use as well.
Yes, I mentioned before. So this is the software CCD Stack 2. So CCD Stack 2 basically is more specialized
One second.
towards images.
Sorry to cut you, but you'll have to switch your screen in the screen sharing because it is still showing us your PowerPoint presentation. You'll have to
Okay.
go and manually do that.
Is it showing you the software now?
Yes, it is.
Okay, so this is the software CCD Stack 2, and it's more specialized towards images taken from a CCD astronomy camera. But the processes are the same if you took it from a DSLR. All the procedures and the stuff are the same. So this is what a single image looks like. So this is the object in question is the Hubble's Variable Nebula. So this is a nebula around this star over here. And this one image is 15 seconds of exposure. So you can see there's a lot of noise. There's some donuts, which is actually dust particles. And there's a lot of brightness along the edges. So I'll show you the calibration frames now. So this is what a flat looks like in a CCD. So you can see it only has the dust particles focused in. It has the edge glow, and it has the general glow of the sky glow in it as well. So we minus this off the picture and to get our final image. And this is what a dark looks like. So the dark, as I told you before, is where we cover the sensor, we allowing no light to enter, and we just let the sensor run for the same exposure of 15 seconds. And you can see the the hot pixels. So this is basically the noise generated by the camera sensor, the thermal noise, and there's also a gradient between on the sensor, which is a natural gradient present in the in CCD sensors, where you have a brighter area on the edge, and you go on towards a darker side. So what we're going to do in this is that first we're going to calibrate each of these images. So as I'm like moving through the images, these are all individual 15-second exposures, and we have around 250 of these 15-second pictures. So I'm going to go in the process and I will calibrate these images. Now we already have selected the dark image. We have the flat image also selected, and I'm just going to apply it to all, and we will see how it changes the image. So basically what we're going to expect is that the dust should be removed, the dust particles should be removed, the edge glow should be removed, and the general gradient is also will also be removed. So we'll wait for this to process,
While we're
and we'll
waiting,
see our final result.
just some information. This software that you're using, since most of the people here do not have professional PC programs or like proper hard drives or like RAM required, can you share whether this would work on like a normal laptop, or would you require additional specifications for it to be fast, to be a speedy process?
Well, you can run this on any laptop. It won't really make a difference. The only difference will be if you're using images from a DSLR, so you will have more waiting time if you have a slower laptop in processing those images. As you can see down here, we can see that we have 803 megabytes of data right now combined. So if we were using a DSLR and we had like 100 images, then we would be having like 4 GBs of data, 4 gigabytes. So it would require more processing. Anyway, now we can see that the image over here has been calibrated. We can see the dust particles have been mostly removed. There is still some effect that is acceptable. And we can see that the gradient has also been removed, and the glow on the edges of the sensor has also been removed. So our next step, so we can see that all of these pictures, they're not aligned. So they're constantly moving. They're not in one place. So what we have to do is that we now have to align these pictures. So aligning is called registration. So you basically register your data. So in registration, what's going to happen is that it's going to select stars. So it's going to automatically detect how many stars are in an image, and it will select those best stars. And what it's going to do is that it will check every image, and it will find those specific stars in that image, and it will align each image according to those stars. So currently it has selected these stars. And so this is one image on top of the other. It has inverted the image to make it easier for itself. So if we move this around, you can see that the stars are the stars which are selected. It's going to align them. So when we align them, we're going to expect a flat image with no such like differences or some bumps caused in them. So if you click align all, it's going to process each image. So you can see it's aligning them pretty well. So this is usually when you have very good images. So one or two pictures might not get aligned because they have some streaks in them. But most pictures, like right now, is said too few stars matched. This is due to this particular image might be a bad image. That's why it will not align it because it couldn't find all the stars in them. But most images you can see it finds the stars in them, it rotates them around, it rotates the picture, and it moves the picture around as well to kind of align it according to that one reference frame. So as it will finish now. Okay, so these pictures, of course, they won't be aligned. So now we're going to do apply to all, and this will basically apply the alignment process. So now all the pictures will be adjusted accordingly.
And do you have any additional struggles during the process using the software? Are there any problems that you would take note of?
Yes, like sometimes our images are not good. So we have like I'm going to right now find that one those two images which were not aligned, and we'll see why they weren't aligned. So I'm right now scrolling through all the images. You can see that everything's in center, and only the frames are moving around. Right now, this image right here. So this image is the one which was not aligned, and we can see the stars are a bit bloated in it. So we can just simply remove that image. And now we're going to find the other image which was not stacked as well, and remove that so we don't have any problems in our data, in our final image. So you can see the alignment worked pretty well as I'm moving through the frames and everything is in its position. Also, fun fact over here, you can notice this one line going through the image. That's actually a satellite passing through. So satellites offer a pretty big problem. Not much of a problem, but like these days, this is also a satellite like streaking through the image. due to the onset of Starlink, we have a lot of satellites these days in space, which come in our images. So I'm just going to move through all these pictures. So I think all of these have been aligned properly. Now our next process is that we are going to normalize this image. So what normalize does is that you select a dark portion of the of the image, and you're just going to it's going to match that darkness with each image so that you don't have any problems with the background of the image. So now that it has been normalized, we can just combine them. Now, they're different processes, they're different types of stacks, but what we usually use is a median stack. So as I click this, we will have our final stacked image come up here. So you can see that it has brought out all the nebulosity. So this is a combination of 250 15-second images, and that accounts to around 1 hour of exposure. And if you compare it with the single image, you can see how much of a difference, how much of the noise has gone away. And now we just have this clean image which has formed over here. Now you can take this into Photoshop as well. And I'll switch the screen to Photoshop and show you what we do in Photoshop. So when you load it into Photoshop, you will get something like this. So you will see that it's not the same as how we saw it in the previous place. This is because Photoshop does not stretch the image. So there's something called stretching where you bring out the data. So we're going to open levels, and we're just going to push this back. So this line over here, this big peak, that's where all the data lies, where our nebulosity is and all the stars and stuff. So we're going to open curves, and we're just going to do some stretches. So our data is over here. And what we need is that we need to amplify the curve over this data. So the different kinds of stretches. So this is one kind of stretch where you can see the curve has been moved onto the peak, and you can see the brightness has increased. And now we're just going to push the levels back a bit to focus. We're just going to focus on this peak. So we want this to be stretched out. We're going to do another curve stretch, and you'll see how it changes. And you move the levels back a bit again. And we now have a similar image to the one we saw in the software earlier. Now there is some unevenness in this image. There are some darker areas, some lighter areas. So if we select it all, copy it out, and make a new image, so we can remove the background brightness from here even using this process, which I'm going to show you. So if we take the healing brush tool from Photoshop and we select any general area, so we can remove this nebulosity at first. So because we don't want the nebulosity to be affected. We just want to isolate the background of this image. So we're going to just rub this out. And this is, I guess, a good enough representation. So now what we're going to do is that we're going to take this select filter, go to noise, and there's this noise effect called dust and scratches. So if we select this, what it basically does is that it will remove the it'll remove the stars, and it will only kind of isolate the background in this image. So if we take dust and scratches to roughly around this much, so we can see now we have only the background in this picture. So if we compare it with this, so we have everything in here, but now we just isolated the background. So I'm going to also blur this a bit so it does not add more noise into our image. So I'm going to do a small Gaussian blur, and now we have this kind of a background image. Now Photoshop has this nice thing where we can apply an image on top of the original image. So what we're going to do is that we're going to select that file, the background data only, and we're going to subtract it out. So what it's going to do is it's going to minus that out of the image, and now we have an even background. And if we adjust the levels again, you can see now that the background has totally gone. So we have an even background, and there's no more of these weird contours present over there. Now you can further denoise this a bit. You can despeckle it to remove some of the grains in it. And then you can also change the brightness and the contrast to kind of bring out more of the details. So if you increase the brightness and then increase the contrast. So you can consider this like kind of a final image which has been processed. And if we compare this again with the final image shown over here using the software earlier, you can see we kind of totally eliminated the contoury background, and we have successfully brought out the nebulosity in this image. So this is like the a pretty general overview of how astronomy images are taken and how they're processed using these various softwares, and how then you use Photoshop to do the final adjustments. And these are kind of scientifically relevant images as well. Like even though you're doing all this tweaking, as long as you don't add or remove data from the image is scientific and it has a certain amount of data in it. So yes, this is pretty much all I had to share with you guys today.
Before
We've
we
been
move on to question and answers, on the topic of publishing photography or participating in astrophotography, do you have any names of places or societies in Pakistan or even abroad that would be looking for people who are willing to submit their own works?
there's not really places who are wanting people to submit pictures, but there are like astronomical societies like the Lahore Astronomical Society, the Karachi Astronomical Society. So these are places on Facebook where people submit their work, and they generally where people share all the work they've done, all the pictures they've taken, and they're really, really great, like people who do really good astrophotography of our night sky using the difficult conditions of our local Lahori skies or the skies of Islamabad, which are pretty light polluted. So despite all that, they managed to like cut all that out and take really perfect images.
And
So yeah,
about light pollution, prior to moving to IST for university, you were using your own telescope here in Lahore. Do you think there's been an improvement because you now have access to better technology over there, or do you think that amateurs can make something out of the bare minimum that they have available to them as well?
yes, definitely amateurs can make out the bare minimum. So like this image over here, this was taken just using my DSLR, not even without a telescope, and you can still see the nebula has shown up in it. So of course, before I had access to these kind of telescopes, I still used to take pictures of the night sky, and you can still take the pictures of the Milky Way as well, which is like a pretty big uh, you don't require telescopes for that. You can just point your camera and gather the information and stack it and remove all the excess material and get out that the Milky Way's band in the sky. And you can do that using just a DSLR camera. These days, people are also using their smartphone cameras to, which also somehow have started taking exposures, and using that, they take pretty good images of the night sky. So anything that basically has stars in it or has some kind of an astronomical object is considered an astrophotograph. So yes, anyone can do it. I specifically did. Of course, when you have telescopes, you can go into the more deeper objects like these, and you can like go into the much more smaller objects and the fainter objects. But still, anyone who wants to start astrophotography on their own can do it, even with just a smartphone.
And what about the time it takes to capture all of these photos that you required stacked up in the end?
So like if you have a night of imaging, you can like spend like I practically personally spend from like 6 p.m. to around 8:45 and I in that time I can gather around 1.5 hour of images.
I see.
So like you have like 6 and 8, 2.5 in like around 3 hours you can get like half the amount of time in images. So it is time taking, and you have to stand in the cold or in the hot, or and it's tiring as well. But in the end, when you get these final results, it is worth it, I guess.
Additionally, are you encountering any problems with your astrophotography right now? Parts of it that you may want to improve, things you want to do better with your own work?
Yes, because currently I don't have access. So the next step in astrophotography using an astronomy camera is that you use narrowband filters. So narrowband filters are basically like these certain wavelengths which you can tune into to get more specific kind of data from objects. So you have like the hydrogen alpha line, you have sulfur 3 line, and you have the oxygen line. So these are like the three main filters which are used in images you see from the Hubble telescope. So that's the color palette of the Hubble telescope, the sulfur, hydrogen, and oxygen wavelengths. So people who have those filters, they produce pretty amazing images as well, because you narrow down only on those certain kind of features which are like throwing out that light. So yeah, we don't have those right now at our university, but hopefully we will get those soon enough, and then we can start using those as well.
If anyone else has any questions that they want to ask, especially the people in the chat, Anas bin Tahir asked if you have to use software for these photos, and you've already answered that question. You use Photoshop and the stacking program. Does anyone else have a question for Shahid? If not, then I will move on and ask a couple of final questions before we end. Ihtisam has a question. Please give some information about black hole imagery, Shay.
So black holes cannot be imaged from the ground or using any any good telescope out there. The only way they imaged the black hole recently was using the radiation which comes out of it, which is a very specific wavelength of infrared. I'm assuming it's infrared, because it's pretty difficult to image black holes. You can't really see the object itself, but you can see what it's doing to the things around it. So that's like how the image of the black hole was formed.
Dr. Sayed has mentioned that Sri Lanka has state-of-the-art planetariums. What do you think about Pakistan? Do we have a need for more planetariums or more opportunities for people who want to photograph the skies?
So planetariums are more like where you have displays of planets and you have a projector where you can see the night sky and stuff. But like observatories, in terms of observatories, we have one at IST where people come and do their researches, and we have the biggest institute on telescope right now over here. Other than that, we have some private observatories where work is being done, but there is not any other like big kind of such observatory where the public can easily have access to.
I see. Another question is here. Sayyida Fatma is asking, when you stack photos, is there a specific requirement of images to stack?
So yes, the requirement is basically how bright the object is. So if you have a very dim object, you would generally go for a more number of images so you can get a longer exposure on that. So if you have an image like a galaxy, you would be looking for 3 to 4 hours of images. If you have a very dim nebula, similarly, you'd be going for like 5 to 6 to around also 10 hours. People also have gone to around 72 hours of combined exposures. But if you have brighter objects, you can like keep it down to around 15 minutes. Anything which is more feasible to your equipment and your own time frame, so you can manage that.
Okay, does anyone else have any questions? While we're waiting for someone to maybe send another question, I personally have one question for you right now. Is there a specific thing that you're wishing to photograph in the night sky?
Well, it's not one thing. There's like a whole list of things which I want to photograph. And since like we have the timing, so like the our observatory gets closed at around 9 p.m. So there's not like much I can image in one night. So we have to move our sessions of imaging over many nights. There's also one object which I imaged for over 2 weeks, and I got in the end like 4 hours of data on that. So yeah, there's like pretty much everything which I want to to image in the night sky.
Okay, Saida Fatma is asking, how did you get to know about astrophotography? Basically, how did you make the jump from your previous passion in astronomy to astrophotography? What made you want to do it? And what benefits do you think it brings to you?
So astrophotography generally, naturally, as if you have an interest in astronomy. So if you have an interest in using telescopes, then astrophotography comes along with it because visual astronomy, using your eyes to see things through the telescope in city skies, is pretty much useless. And this is what I personally believe. You can only see the planets in the city skies with the telescopes, and you can't see anything else. So to see those other things, you need the skills of astrophotography to bring out those other objects in the night sky. So that's how like one goes towards astrophotography.
Do you think it brings any form of benefit if someone wants to pursue this as a career or as a hobby that may bring in some form of credibility to them? Are there any such benefits?
There is benefit because scientific imaging is how astronomers basically do their research. So images are basically data, and the process of taking astrophotography is basically how these kind of all our scientific images, all our data is acquired, and how all those researches are done. Because each pixel is a value, is a number, and all those things can be researched upon, and you can do a lot of different things in astronomy and astrophysics using this data, which is captured through astronomy cameras.
I see. There's another question. Are these exotic colors that we see in astrophotography of nebulae, are they real or do we add them to identify them?
So in my image on the top left, this is real color. So this is how it really looks like if you had very, like if it was pretty close and you were in a space and looking at it. But the pictures from Hubble, those are taken, as I told you, in the SHO color palette, which is the sulfur line, the hydrogen line, and the oxygen line. So those specific wavelengths, those are added into the red and the green and the blue channel to create artificial color. So the Hubble images are not true color, but these optical images which you take from RGB filters are true color.
Okay. Another question is that since this is a niche field in Pakistan, do you think this field in overall is steadily growing now, or is there some sort of stagnation present?
Well, generally, I don't know if how much research into astronomy is going on in Pakistan. There is some research in astrophysics and stuff going on in my university, IST. But generally, in that, I would say that it is pretty much stagnated.
I see. I think that's all for questions. Oh wait, no, there is one more. There's three more. um, what would you recommend if someone wants to start for beginners? Can you see the chat, Shay? I think.
Yeah, I can see the chat.
Okay, yeah.
So, for people, for someone who wants to jump into astrophotography, so the telescopes are pretty expensive, but you can get a decent equipment for around, I think, five $5,000, and you can get a mount in that. You can get a telescope, and you can get the camera which is required to take such images. But this is $5,000 is still a lot because people are doing much more with much less. So if you have any kind of an equipment which has a tracking mount, and you have a telescope and you have a DSLR, then you can do astrophotography. And you can do that in around $1,000 as well, and even lesser than that if you have
I see.
certain equipment. But of course, it is difficult to get. It is not that difficult to get in Pakistan, but the customs again, they do add the costs. They do add costs into importing stuff. So any suggestion for a camera, because they're easy to get for cameras? If you get like Nikon D7000 series, so those are good for astrophotography. But generally, I'd recommend to use the astronomy cameras. So, like the one I'm using, this box on the right. So this one in 2005 it cost $1,800. So it was an expensive camera at this time, and S big cameras usually are expensive. But these days, there are people who locally import telescopes. So there's Sahal telescopes and binoculars in Karachi. So they have imported a shipment of, and also sold by now. So they brought these 8-inch telescopes into Pakistan, and they cost around 4 lakhs, and they sold astronomy cameras as well, which were like 30,000 each. They were actually planetary cameras, but you can still do a lot with planetary cameras as well. So yeah, you can check out their websites. I mean, their Facebook page, Sahal Telescopes and
Yes.
Binoculars, and they have that stuff on their page for anyone who wants to locally buy stuff
Okay.
in Pakistan.
There's one more. There's two more. How can I develop interest of space in kids? And there's also one that asks you to tell the difference between satellites and stars.
Well, if you're looking at a star, it will remain at the same position. But if you have a satellite, so it will kind of create a streak through your image. So I earlier showed a picture where there was a streak going through my image. So that was a satellite, and the stars are pretty much stable and stagnant in their positions. And to develop interest in your kids, you will have to like get them into documentaries, books, and generally, if they are interested in this kind of stuff, don't force them, of course. But like, there's a lot of resources on the internet. There's a lot of resources on YouTube, and there are these magnificent pictures which one can show to kind of develop an interest.
All right. I think that's all for questions. Is there any closing statement that you want to make, Shay, before you leave? And before we go into that, just want to mention that this is being recorded and we will try our best to get this uploaded onto YouTube or Shahid's Instagram so that people may be able to refer back to it when they're trying their own hand at astrophotography. Yes, Shay.
Closing statements more like that astrophotography, as I said, is a game of patience. So if you're impatient and you want results as quickly as possible, you won't get those desired results. So in science and in data collecting, one also always has to be patient when collecting their data. And this is like kind of a basic quality one should have when doing science. So yes, I guess that's all from my side. Thank you a lot for joining, and I hope you guys learned a lot. Well,
Thank
not
you
a
so
lot, but
much, Shay.
about the basics of how images are processed in science.
Thank you, Shay, for joining us today and helping us get an introduction into astrophotography. We do hope you will be back to teach people in more depth, maybe later on in the future. But for now, this is all. Thank you for your questions. Thank you for your participation. This will be uploaded maybe in 1 or 2 days to Shahir's social media platforms. Thank you. Goodbye.